Hello, my name is Daria Tarutino and I'm research assistant at the Institute of Smart Systems and Artificial Intelligence. Today I'm going to present our work OpenThermalPose and open source annotated thermal human pose dataset and initial YOLOv8-Pose baselines. In the field of computer vision, human pose estimation, or HPE, is a crucial task that focuses on identifying the position and orientation of the human body across images or videos. This process involves the detection of distinct anatomical landmarks, including the shoulders, wrists, knees, eyes, nose, ears, ankles, and arms. HPE has extensive applications across various sectors. It enhances the capabilities of action recognition systems, supports advancements in robotics, enriches augmented reality experiences, aids in sport analytics, and plays a significant role in healthcare. HPE can be carried out in both 2D and 3D dimensions. For 2D, HPE the techniques estimate the location of body key points in two-dimensional space as they appear in image or video frames. These methods can be broadly categorized into two types: single-person pose estimation and multi-person pose estimation. Single-person pose estimation approaches include direct regression and heat map-based methods. On the other hand, multi-person pose estimation can be approached via top-down or bottom-up methods. Top-down HPE approaches begin by identifying humans within an image using a detector, and then proceed to predict the key points within the confines of the detected bounding boxes. Examples of systems that utilize this approach include YOLOv8-Pose, YOLOv8-Pose, and AlphaPose. Conversely, bottom-up methods start by predicting each key point independently across the entire image. These key points are then grouped to form individual poses, as seen in systems like HRNet, OpenThermalPose, and CenterNet. To train these HPE models effectively, it's crucial to use large-scale labeled datasets. These datasets must contain a wide variety of poses, closing depths, occlusions, and lighting conditions to ensure robust and accurate pose estimation. There are three key datasets: Max Planck Institute for Informatics Human Pose Dataset, Microsoft Common Objects in Context COCO dataset, CrowdPose dataset. They feature RGB and grayscale images which capture the visible light spectrum. However, this visible domain encounters challenges like poor illumination and privacy concerns. Thermal imaging technology, which operates at longer wavelengths, addresses these issues effectively by being insensitive to lighting conditions and maintaining privacy through the capture of heat signatures rather than visual details. HPE models trained on RGB datasets perform poorly when applied to thermal images, largely due to significant difference between these imaging domains. Furthermore, there is a scarcity of publicly available thermal datasets for training HPE models. To bridge this gap, we have developed OpenThermalPose and open-source thermal human pose dataset. This dataset includes labeled bounding boxes and 17 key points and encompasses a diverse range of conditions from both indoor and outdoor environments. Mehra et al. Created a dataset of consisting 1,000 annotated thermal images with bounding boxes and 5 key points, using this for training, validation, and testing phases. The thermal pose dataset includes 24,000 low-resolution thermal images paired with RGB images, used to derive 19 key points from the RGB images for thermal image labeling, but lacks bounding box annotations. The SLP dataset, focusing on in-bed poses, features 14,715 thermal images from a controlled indoor environment, annotated with 14 key points per image, but without bounding boxes. The UCH thermal pose dataset comprises 904 thermal images with 1,378 human instances annotated with bounding boxes and 17 key points aimed at both training and testing. In contrast, our OpenThermalPose dataset significantly expands available data with 6,090 thermal images from varied environments, annotated with 17 key points and bounding boxes, making it the most comprehensive thermal HPE dataset currently available, particularly notable for its diversity and scale. For our data collection, we utilize the Guide C640 Pro thermal camera featuring a resolution of 640 by 480 pixels in a room with controlled temperature and lighting. The process was divided into 2 main sessions. In first session, 14 participants, 4 females and 10 males, executed 15 basic sport exercises in 2 views, frontal and side, producing 2 videos per exercise with 10 repetitions each, totaling 420 videos. The second session captured 15 different actions involving pairs of subjects, with 8 unique duos participating, resulting in 120 videos. From these sessions, we extracted and manually selected 2,000 frames showcasing a variety of poses. Additionally, the team has a dataset with real-world variability. We integrated frames from our thermal faces in the YOLOv8-Pose dataset developed for facial detection and localization in thermal imagery. This dataset comprises 9,982 images of 147 subjects captured using a FLIR T540 Pro camera with a resolution of 464 by 348 pixels in diverse indoor and outdoor settings. Specifically, we utilized 4,090 outdoor images from this set, featuring 15 subjects in different locations and weather conditions. Ultimately, our OpenThermalPose dataset encompasses a total of 6,090 thermal images, 2,000 from indoor sessions and 4,090 from outdoor scenarios, reflecting a broad spectrum of environments and activities. We annotated our dataset with bounding boxes and 17 anatomical keypoints in alignment with the COCO dataset format. Initially, we used the largest model of YOLOv8-Pose pre-trained on COCO for automatic labeling. Subsequent refinements were made manually by our moderators using LabelMe software. Each keypoint was also marked as 0 for occluded or 1 for visible. The dataset was structured into 2 distinct sets for training, validation, and testing. The first indoor session includes images of 14 subjects divided as 11 for training, 1 for validation, and 2 for testing. The second session comprises 8 experiments with 6 designated for training, 1 for validation, and 1 for testing. The outdoor set from the thermal faces in the YOLOv8 is already segmented into training, validation, and testing images. YOLOv8-Pose, a leading model in object detection, with extensive configuration from nano to extra-large sizes, shows comparable performances to state-of-art models on the COCO dataset. These models are versatile, supporting various conversion formats like ONNX runtime and TensorRT, and allows straightforward training, validation, prediction, and expert functionalities. We also incorporated the YOLOv8-Pose dataset in our evaluations to test the robustness of our dataset. This dataset shares the same annotation structure and includes 600 training images, 200 validation images, and 104 testing images. We conducted 3 experiments, training YOLOv8-Pose solely on YOLOv8-Pose, solely OpenThermalPose, and on a combination of both. The evaluation were performed on both sets, utilizing a DGX7 equipped with 8 NVIDIA A100 GPUs. We present the accuracy results for the 5 YOLOv8-Pose models across 3 experiments using metrics like AP50 and AP5095 for bounding boxes and keypoints. Results for the OpenThermalPose dataset are detailed separately for indoor and outdoor environments, with standout performance highlighted in bold. The YOLOv8-Pose model, the most compact version initially trained on the YOLOv8-Pose dataset, achieved AP50 bounding box scores of 99.49%, 97.87%, and 98.76% across the indoor, outdoor, and YOLOv8-Pose test sets, respectively. Training on the OpenThermalPose dataset improved these scores to 99.50%, 99.32%, and 99.35% for the same environments. A similar pattern was observed with the pose estimation accuracy with AP50 scores, improving from 97.92%, 91.64%, and 89.75% to 99.50%, 94.20%, and 97.59% respectively. Further enhancements were noted using AP1595 metric, particularly when the models were trained on the OpenThermalPose datasets compared to UCH-ThermalPose. For example, the YOLOv8-Pose model showed increases from 80.46%, 77.69%, and 79.71% to 95.71%, 88.62%, and 86.16% in AP1595 bounding box scores. The largest model, YOLOv8-Pose, also saw significant improvements, with AP1595 pose scores rising from 87.14%, 79.14%, and 79.13% to 96.06%, 90.61%, and 81.52% across the test sets. The figure presents a comparative analysis of the YOLOv8-Pose models trained on the UCH-ThermalPose, OpenThermalPose, and a combination of both datasets. The figure illustrates that model trained on our OpenThermalPose dataset consistently outperforms those trained solely on the UCH-ThermalPose dataset across all tests and metrics. This underscores the superior effectiveness of the OpenThermalPose dataset. Furthermore, models trained on the combined datasets exhibit slight improvements compared to those trained only on OpenThermalPose. This enhancement is likely attributed to the larger size and richer annotation diversity of our dataset compared to UCH-ThermalPose. Now, regarding qualitative results, we used two YOLOv8-Pose models to run predictions on image from the test sets. The first session of the indoor set of OpenThermalPose, the second session of the indoor set of OpenThermalPose, the outdoor set of OpenThermalPose, and UCH-ThermalPose. We use the original YOLOv8-Pose model trained on COCO to run predictions on RGB images with low illumination. Then we apply the YOLOv8-Pose model fine-tuned on our dataset to corresponding thermal images. Now, squat workout monitoring demo. So first is YOLOv8-Pose trained on the COCO dataset. Now, YOLOv8-Pose fine-tuned on our OpenThermalPose dataset. Now, YOLOv8-Pose fine-tuned on our OpenThermalPose dataset. In this study, we introduced the OpenThermalPose dataset, a comprehensive thermal human pose dataset consisting of 6,090 images with detailed annotations for 14,315 human instances. This dataset supports both single and multi-person pose estimation tasks. Our extensive testing with YOLOv8-Pose models demonstrated the dataset's robustness, with models trained on OpenThermalPose showing superior accuracy in both our dataset and the external UCH-ThermalPose dataset. We have made the dataset source code and pre-trained models publicly available to further research in this field. Plans for future work include expanding the dataset with more data collected under diverse environmental conditions. Thank you.